Welcome to this session. As we have discussed in the last class, we will be discussing the non-trivial solution of a standard eigenvalue problem, and I will be taking, we have already looked into the solution by considering the Dirichlet boundary condition. So, in this class we will be looking into how the solution evolves in case of Neumann and Robin mixed boundary conditions. So, d square y dx square plus lambda y equal to 0 subject to at x is equal to 0 dy dx is equal to 0 and at x is equal to 1 y is equal to 0. So, both are homogeneous boundary condition, but the condition at x equal to 0 is a Neumann and the condition at x equal to 1 is a Dirichlet. Now, let us look into this type solution of this type of equation. Now, again as we have discussed earlier, lambda can be 0, can be negative, can be positive. Now, I am not going into detail by solving the sub cases 0 and minus alpha square, negative lambda and 0, because they will be giving a trivial solution. So, it is up to the reader, just take it as an assignment to show exactly going by the same way whatever we have done earlier, to show that if lambda is equal to 0, we are going to land into a trivial solution. Similarly, if lambda is negative, then also we will be getting a trivial solution. So, we will be solving a case where we will be getting a non-trivial solution for lambda equal to positive or plus alpha square. If you do that, we will be getting d square y dx square plus alpha square y is equal to 0, and this, as we know that this has a solution y is equal to c1 sin alpha x plus c2 cosine alpha x. Now, let us write down the first boundary condition at y is x equal to 0, dy dx equal to 0. So, therefore, we take the derivative of y with respect to x. So, this becomes c1 alpha cosine alpha x minus c2 alpha sin alpha x. Now, dy dx equal to 0 at x is equal to 0. So, first boundary condition at x is equal to 0, dy dx will be equal to 0. So, this will be 0, x equal to 0, cos 0 is 1 and sin 0 is 0. So, we will be having c1 alpha is equal to 0. For alpha non-trivial solution, alpha is not equal to 0, that means c1 is equal to 0. So, therefore, we will be having y is equal to c2 cosine alpha x as the solution. Next, what we will be doing? We will be utilizing the other boundary condition, that is residing at x is equal to 1. So, y is equal to 0 at x is equal to 1 as well. So, therefore, what is the y? Y is equal to c2 cosine alpha x. So, therefore, this becomes 0 is equal to c2 cos alpha. Now, there are two options, as we have discussed earlier, either c2 equal to 0 or cos alpha is equal to 0. If c2 is equal to 0, then we will be again getting into a trivial solution. So, c2 is not equal to 0, therefore, what is option left is cosine alpha is equal to 0. And what is the general solution of cosine alpha equal to 0? Alpha n is equal to 2n minus 1 pi by 2. So, these are the roots where the cosine alpha equal to 0. So, eigenvalues are 2n minus 1 pi by 2, and what are the corresponding eigenfunctions? Corresponding eigenfunctions were c2 cosine 2n minus 1 pi by 2 times x. These are the eigenfunctions, or we can write it at c2 cosine alpha n x, where alpha n is equal to 2n minus 1 pi by 2. In the next example, we will be taking up the boundary condition as a mixed boundary condition at x is equal to 1. It is a Robin mixed boundary condition, and see how the solution evolves out. D square y dx square plus lambda y is equal to 0, at x is equal to 0, we have y is equal to 0, and at x is equal to 1, we have a mixed boundary condition, that is dy dx plus beta y is equal to 0. Both boundary conditions are homogeneous, but in this case the boundary at x is equal to 1 is replaced by a Robin mixed boundary condition. So, again we can have three cases of lambda. It can be 0, it can be negative, it can be positive. As we have discussed earlier, 0 and negative value of lambda will be leading to a trivial solution. We are not interested into a trivial solution, we are interested in a non-trivial solution, and let us look into how this non-trivial solution will arise in this case. So, d square y dx square minus alpha square y is equal to 0 plus alpha square y equal to 0, it is a positive. So, therefore, we know the solution y is equal to C1 sin alpha x plus C2 cosine alpha x, and x is equal to 0, y equal to 0. Let us apply the first boundary condition, y equal to 0 at x equal to 0, the sin 0 is 0. So, this will be C2 cosine alpha x, cosine alpha. Okay. Now, cosine alpha will be not equal to 0. So, therefore, C2 will be equal to 0. So, we have the solution as C1 sin alpha x. Now, let us put the other boundary condition at x is equal to 1, dy dx plus beta y equal to 0. So, what is dy dx? Dy dx will be nothing but C1 alpha cosine alpha x. So, at x is equal to 0, dy dx will be C1 alpha cosine alpha x plus beta y, beta times C1 sin alpha x. So, this is the solution of y. Now, beta times C1 sin alpha x should be equal to 0 when the full thing is evaluated at x is equal to 1. So, let us do that. C1 will be common, alpha cosine alpha plus beta sin alpha is equal to 0. Now, if C1 is equal to 0, the solution is y is equal to C1 sin alpha x. If C1 is equal to 0, then again we will be landing up in a trivial solution, that has to be avoided. So, in order to do that, for non-zero C1, the other term in the bracket will be equal to 0. So, C1 cannot be equal to 0. So, therefore, alpha cos alpha plus beta sin alpha should be equal to 0. So, what is that? This becomes now alpha plus beta tan alpha is equal to 0. Now, unlike the earlier two cases where we had a distinct expression, we have an explicit expression of eigenvalues. For example, in the first case we had n pi as the eigenvalues and sin n pi x are the eigenfunctions. We had the distinct solution, we have the explicit solution of the eigenvalues. The first case the eigenvalues had assume the values n pi. In the second case, in the case of when we had a Neumann boundary condition at x equal to 0, we had the 2n minus 1 pi by 2 are the eigenvalues. Now, in this case we are not getting an explicit expression for the eigenvalues, we will be getting a transcendental equation. Roots of these transcendental equations will be the eigenvalues of this problem. If you really plot this function as a value of alpha, this transcendental equation, you will be having the solutions like this. There will be infinite number of solutions where they cut the x axis or alpha axis. Each of these alphas will be the eigenvalues for this particular problem. So, roots of this transcendental equation and are eigenvalues. So, we denote as them as alpha n plus beta tan alpha n equal to 0. So, how these roots will be evaluated? These roots can be evaluated by using a Newton-Raphson technique. So, what are the corresponding eigen functions? Corresponding eigen functions will be Cn corresponding to nth eigenvalue is C1 sin alpha n x, where alpha n are the roots of this eigenvalue problem. Now, let us look into the let us summarize whatever we have done for a standard eigenvalue problem. Okay. So, let us put down the boundary conditions and then we put down the eigenvalues in the next column. In the third column, we write down the eigenfunctions. If we have Dirichlet boundary condition at x equal to 0 and x is equal to 1, we have y equal to 0, then eigenvalues are n pi and eigenfunctions are sin n pi x. If the boundary condition at x equal to 0, dy dx is equal to 0, that means a Neumann, and at x is equal to 1 we have a Dirichlet, then 2n minus 1 pi by 2 are the eigenvalues and cosine functions are the eigenfunctions. In case of boundary condition at x equal to 0 is y equal to 0 and x equal to 1, we have a mixed boundary condition dy dx plus beta y equal to 0. The eigenvalues will be the roots of transcendental equation of alpha plus beta tan alpha is equal to 0, alpha n basically nth eigenvalue, and the corresponding eigenfunctions are sin alpha n x, where alpha n's are the roots evaluated from this transcendental equation. So, this table summarizes the various values and of various eigenvalues and eigenfunctions, how they alter into for different types of boundary conditions. So, these are the standard values. If you have let us say a boundary condition, instead of x equal to 0, you will be having at x is equal to 0, y is equal to 0 and x is equal to 1, dy dx equal to 0. So, in that case, suppose these boundary conditions are reversed. For example, the boundary at x is equal to 1 is insulated, that means dy dx equal to 0 there, and boundary at x is equal to 0 is homogeneous, that is y equal to 0 at that boundary. So, in that case, we will be having a change of coordinate by defining a new x star as 1 minus x. So, that again it will be after in the transformed coordinate system, it will be the boundaries will be falling into the standard boundary conditions like this, and we will be having the eigenvalues and eigenfunctions in this form. So, these are the various types of boundary conditions we will be encountering, and the eigenvalues and eigenfunctions will be changed accordingly. So, in the next we will be looking into the some forms of spatial functions, which will be quite frequent in various separation of variable type of solution of partial differential equations. Now, let us look into the spatial ODEs, some more spatial ODEs. For example, the first one is the ODE is like 1 minus x square y double prime. Y double prime is basically d square y dx square, and y prime is dy dx. 1 minus x square y double prime minus 2 x y prime plus n into n plus 1 times y is equal to 0. So, boundary conditions are at x equal to plus minus 1, y equal to 0, and n is non-negative integer. if that is the case, if this is a type of equation we are going to have, and this is a type of equation boundary conditions we are going to have, then the solution is in the form of C1 Pn x plus C2 Qn x, where Pn is known as the Legendre polynomial and Qn is known as the Legendre function. Now, this type of equations one will be encountering whenever we are talking about the spherical polar coordinate system. Okay. So, the previous one that we have discussed, d square y dx square plus lambda square equal to 0, those will be one will be encountering whenever we are talking about a Cartesian coordinate system. So, if you talk about the spherical polar coordinate system, you will be encountering this type of equations. Now, the solution will be consisting of Pn, the Legendre polynomial and Legendre functions. Then let us look into some of the properties of Legendre polynomial. There Pn at 1 will be is equal to 1, Pn at minus 1 is equal to minus 1 raised to the power n, minus 1 to plus 1 Pn square x dx is equal to 2 divided by 2n plus 1. Pn, the Legendre polynomial, it satisfies the orthogonal property. Pn satisfies the orthogonal property, that is minus 1 to plus 1 Pn x and Pm x will be equal to 0 for m not equal to n, and m and n are integers, both m and n are integers. Okay. The property of Qn is such that at x equal to plus minus 1, Qn is unbounded. Okay. So, what does imply? This implies, if you look into the solution of this, since the domain of x is varying from minus 1 to plus 1 and at the boundaries minus 1 to plus 1, Qn is unbounded. This simply physically implies that the associated constant, because we are going for a bounded solution. If bounded solution is divided into two parts and one part goes to unbounded or in at a particular boundary, then the whole solution becomes unbounded in that case. So, therefore, the associated constant must be equal to 0. That means, C2 must be equal to 0 in order to have a realistic solution, because at the boundaries the solution goes unbounded. As I said earlier, that the solution of the governing equation is valid within the control volume at every point of control volume as well as on the boundary. If the boundaries the solution becomes unbounded, that is not tenable or agreeable, therefore, the associated constant has to be equal to 0 in that case. Okay. Then we will be we look into the several type of expressions of P0 and others, higher order Legendre polynomials. P0 x, they may be of use. P0 of x is equal to 1, P1 of x is equal to x, P2 of x is equal to half 3 x square minus 1, P3 of x is equal to 1 by 2 5 x cube minus 3 x. Okay, so there are various types of, one can go into any standard mathematics book and into the tables which will be appearing in the first year, for example Krejcik, Grewal. There you can get into the chapters of Legendre polynomials and can know about various other properties of the Legendre polynomial and Legendre function. I have just jotted down or noted some of the important properties of Legendre polynomial and Legendre function we will be encountering with. Next, we are going into the cylindrical coordinate system, because in most of the engineering applications we will be talking about the heat transfer, mass transfer, momentum transfer, or any transport processes occurring in a tube or in a pipe. So, in that case the cylindrical polar coordinate system becomes very, very important, and in the cylindrical polar coordinate system we will be encountering the Bessel equation and the corresponding Bessel functions as the solution. Now, let us look into the Bessel equation. This will be basically for cylindrical coordinate system. The differential equation that one will be encountering in this form, x square y double prime plus x y prime plus x square y will be equal to 0. And if that is the case, the solution will be in the form of C1 J0 x plus C2 Y0 x. If for differential equation, if one encounter as x square y double prime plus x y prime plus x square minus alpha square times y, where alpha is an integer. So, therefore, solution is in the form of y of x is C1 j alpha x plus C2 j minus alpha, or we call it y alpha x, where alpha is an integer. So, j alpha is known as the Bessel function of first kind of order alpha, and y alpha is known as the Bessel function of second kind of order alpha. So, if this is the form, this is we are talking about a 0th order Bessel function and 0th order of first kind and second kind of Bessel function. Now, let us look into the some of the properties of the Bessel function. Those will be quite important. The first property is that y alpha is unbounded at x is equal to 0, and therefore, the whenever we will be coming across to this type of equation where x is basically from 0, x is basically varying from 0 to 1 in the domain 0 to 1. So, the associated constant must vanish. So, in case of solution in the cylindrical polar coordinate system. Second important property of Bessel function is that J0 and J alpha, J0 and in general J alpha is bounded, that they will be having a finite value bounded at x is equal to 0. That means, if you plot j 0 or j alpha as a function of x, this will be the plot of j 0 and this will be plot of j 1. That means, in general j alpha will be oscillating about the x axis n number of times. So, therefore, whatever the every point j alpha, whether it is 0 order of alpha 0, 1, 2, 3 anything, they will be oscillating about the x axis and cutting the x axis infinite number of times, and each and every cutting point is basically a root of the transcendental equation or the eigenvalue of the system. So, j alpha x will be having 0, and since it will be cutting infinite number of times. So, there will be infinite number of roots are obtained of this equation. So, each of these root is basically an eigenvalue to the system. Okay. So, next we will be just looking into one more type of Bessel equation, x square y double prime plus x y prime minus x square plus alpha square times I times y equal to 0. So, the solution is y x is equal to C 1 I alpha x plus C 2 k alpha x, then I alpha is known as modified Bessel function of first kind order alpha, and k alpha is modified Bessel function of second kind of order alpha. The important property is that k alpha is unbounded at x is equal to 0 and I alpha is bounded at x is equal to 0. That means, for a domain x lying between 0 and 1, the corresponding constant of k alpha will vanish, and you will be getting the solution of y x is equal to C 1 I alpha x, and I alpha again it cuts the x axis in n number of times corresponding to n roots or the eigenvalues of the system. The final special function that we will be talking about is Euler's equation. In some of the mathematical problems, you will be encountering this type of equation. If you have an equation in the form x square y double prime plus a x y prime plus b y is equal to 0, then the solution will be in the form of y should be in the order of x to the power r, and you will be having a characteristic equation r. Just put x to the power r in the governing equation, r minus 1 plus a r plus b is equal to 0, and you will be getting a quadratic in r. So, r square minus r plus a r plus b is equal to 0. So, it will be r square minus r 1 minus a plus b is equal to 0. So, you will be having two equations r 1 and r 2, and you will be having the solution in the form of C 1 x to the power r 1 plus C 2 x to the power r 2. So, again by putting the boundary conditions, one can evaluate the constant C 1 and C 2. So, these are the various type of special functions, those will be one will be encountering in solving the partial differential equations using the separation of variables, and different types of eigenvalue problems will be appearing based on the Cartesian coordinate system, cylindrical coordinate system, spherical polar coordinate system, and various kinds of boundary conditions one will be encountering. The solution will differ and the eigen functions and eigenvalues will differ. So, I stop here in this class. In the next class, we will be looking into how to get the adjoint operator given an operator, and how they are connecting to eigenvalue problems or Sturm-Liouville problems, and we will be looking into the various properties and characteristics of the Sturm-Liouville problem before going into the separation of variable type of solution. Thank you very much.